Many weeks ago, when we first introduced the idea of acceleration, we compared what's happening with the Porsche 911 Turbo, which goes from 0 to 60 in 3.4 seconds, and we compared that to my dinky little first car, my 1999 Dodge Neon, I miss you, which went 0 to 60 in 12 seconds. So now that we're talking about energy, we can compare these two cars, and let's just assume for the sake of argument that they have the same mass. Okay, so let's assume these two cars have the same mass. If they have the same mass, then I would say it takes the same amount of energy to get both of these cars to go from 0 to 60. Okay, because the change in kinetic energy for both of the cars would be the same because their change in speed is the same. And if they have the same mass, their change in kinetic energy would be the same. That means the work that it takes to get these cars up to 60 miles an hour is the same. So I could have been happy of and proud of my little Dodge Neon and said, well, look, it uses just the same amount of energy to get up to 60 as the Porsche does, so my little car was just as good as the Porsche. Well, we're neglecting one little fact, which is that my car took 12 seconds to use up that much energy, and the Porsche used that much energy in 3.4 seconds. So there's something very different about the rate that these cars are using the energy and the rate that work is being done on the cars. This uses that much energy in a very short amount of time. So that describes something is very different about this car's engine compared to my car's engine. And that thing that I'm talking about, I haven't named it yet, is called power. So this is one of the last quantities we're going to worry about this week. Power. And the power of this engine is very different than the power of this engine because this engine uses up, its kinetic energy changes in this much time. And this engine causes the car's kinetic energy to change by the same amount in this much time. This car has a lot more power. This engine does. So how are we going to define power? I define it a little different than the book because I think it's such a simple concept, but when you write it out as an equation, it makes it seem complicated. So power is simply how quickly energy is used if you're talking about energy that's being used, or how quickly energy is being supplied if you're talking about energy that's being supplied to a system. And it's such a simple concept that I really like to write the equation in words. And I like to just say power is equal to energy divided by time. How much energy is being used or supplied, and how long did it take for that energy to be used or supplied. So this is what I use when I'm talking about power and calculate anything with power. The official equation from the textbook is this one. P, which represents power, is equal to dW dt, where W is work. So it's like the rate that work is being done. Okay? How fast is the work being done? Did you do 100 joules of work in 2 seconds, or did you do 100 joules of work in 50 seconds? That's going to determine how much power you used. Okay? So again, this looks like a derivative, so you might be like, oh, is W going to be a function of time and I have to take the derivative? No, this is a more complicated equation than you actually need. This is the equation that we really are going to be using, so this is the one I like to focus on. Our units for power are watts, okay? So you've probably heard of that unit. Now we're getting back towards things you've heard of. Watts, you've probably heard of. And 1 watt, according to this equation, this is measured in watts, this is measured in joules, this is measured in seconds. So 1 watt is equal to 1 joule per second. The other reason I don't like this equation is that once you start thinking about how power is measured in watts, I don't want you to see this W, because watt is also represented by a W. I don't want you to see this W and think this has something to do with watts, right? This is work. This happens to be measured in units of watts, which is also represented by W. So anyway, I think this equation is confusing. What does that mean? Let's say we look at a standard light bulb. Let's say we have a 100-watt light bulb. What does it mean to be a 100-watt light bulb? It means that this light bulb uses up 100 joules of energy each second. That's what it means to be a 100-watt light bulb. So let's do a quick example with power and then we'll be done. Because really, I want you to think power is a simple concept. So press pause, try to work through this one on your own, and then press play when you're ready to go through it with me. So I want to know how much power this elevator uses up. I know that it takes 50 seconds to move this elevator this distance. So I want to, since I'm going to say power is equal to the energy used over time, I need to know how much energy does it take? How much work is that motor doing to lift this elevator this many meters? That's the first thing I want to figure out. If I want to figure out how much work the motor is doing, I need to figure out what is the force that it's providing. So this is my free body diagram, and I'm going to write my net force equation, set my net force equation equal to m times ay, and I need to know what my acceleration is. Let's come back up here and see if there's anything that tells me what my acceleration is. Oh, there it is, constant speed. So constant speed means my acceleration is 0. So I can calculate my lifting force. It happens to be the same as the force of gravity in this problem. Okay. Now that I know how big my lifting force is, I can calculate how much work is being done. I can use my very simple equation, work is equal to plus or minus F times D, because this force is constant and we're only dealing with motion and forces in one direction. So I can use that simple equation. The force is pointing up and the object moves up, so I'll choose positive. And the distance d that the object moves is just that delta y of 100 meters. So here I've plugged in the force, here I plugged in the distance the object moves, and I get the work that the motor does. The motor does 980,000 joules of work in order to lift this elevator 100 meters at a constant speed. Now I can come back to my power equation. Power is equal to energy over time. How much energy do we use? 980,000 joules. How long did that take? 50 seconds. So I get that the power the elevator exerts, or the power of the elevator, is 19,600 watts. Another common unit besides watts is a kilowatt, which is just 1,000 watts is 1 kilowatt, so I could also write this as 19.6 kilowatts.